On September 14th, 2015, humanity detected something that should be impossible. That is, everything we think we know about gravity, everything we were taught in school, is fundamentally wrong. The impact was so violent it sent ripples through the fabric of reality itself. Those ripples traveled across the universe for over 1 billion years. And on that September morning, they passed through Earth. For a fraction of a second, every atom in your body was stretched and compressed by waves in space-time. You never felt it, but it happened. Before we dive in, hit the like button and subscribe to this channel, because what you're about to discover will completely change how you see reality. Now, let's dive in. Part 1. The lie we've been told. You've been told since kindergarten that Earth's gravity pulls things down, that there's an invisible force yanking objects toward the ground, that the sun pulls Earth into orbit. Simple, obvious, completely logical. But here's the thing, it's not true. Gravity isn't a force at all. It's something far stranger, far more beautiful, and honestly, kind of terrifying when you really think about it. The Newton chapter. Let's rewind to 1687. Isaac Newton just published one of the most important books in human history, Mathematical Principles of Natural Philosophy. The Principia? Before Newton, nobody really knew why stuff fell, why planets moved. It was all philosophical guesswork and religious explanations. Newton changed everything. He showed that the same force making an apple fall from a tree also keeps the moon orbiting Earth. Mind-blowing for the 1600s. People thought the heavens operated under completely different rules than Earth. Newton unified them. One set of mathematical laws. His law of universal gravitation states, every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Translation? Big things pull hard, small things pull weak. Double the distance, and the pull drops to 1/4. You and Earth pull on each other because Earth is massive. You and that pencil across the room, you're pulling on each other too, but so weakly you'd never notice. How weak are we talking? Get this. If you wanted to build a detector sensitive enough to register a single person walking past it, the detector arms would need to stretch from the sun to Saturn. That's 10 billion kilometers, 6 billion miles. Anything shorter and the signal drowns in background noise. That's why you feel a tiny fridge magnet, but not the gravitational pull of someone standing a meter away. Gravity is 39 orders of magnitude weaker than electromagnetic force. One of physics' deepest mysteries. We still don't know why. But here's where it gets interesting. Newton's equations worked beautifully. For 200 years, they predicted everything. Tides, planetary motion, they even let scientists discover Neptune in 1846 by calculating where an unknown planet should be based on weird irregularities in Uranus's orbit. They pointed their telescopes at that exact spot. There was Neptune. Right where the math said it would be. For 2 centuries, everyone thought Newton had figured it all out. Case closed. But there was one tiny problem. Mercury. The Mercury mystery. Mercury orbits the sun in an ellipse that slowly rotates over time. This is called precession. Newton's equations predicted how much Mercury should precess based on other planets' gravity. The observations didn't match. Mercury was precessing 43 arcseconds more per century than predicted. That's about 1/180th of a degree per century. Incredibly small, but real and measurable. Scientists searched for explanations. Maybe an undiscovered planet called Vulcan was pulling on Mercury. It didn't exist. Maybe Newton's laws needed tweaking. Nothing worked. The mystery haunted astronomy for decades. Until 1915. Enter Einstein. Albert Einstein published his general theory of relativity in November 1915, and everything changed. Einstein's insight was radical. Gravity isn't a force at all. It's the curvature of space-time itself. I know, that sounds like meaningless word salad. Curvature of space-time. What does that even mean? Let's break it down step by step, because this is where it gets wild. Space-time, the fabric of reality. First, forget everything you think you know about space and time. Normally, we think of them as separate, right? Space is where things happen. 3 dimensions: left, right, forward, back, up, down. Time is when things happen. It flows from past to future. Separate concepts. Here's the thing, they're not separate. Einstein showed that space and time are woven together into a single 4-dimensional fabric called space-time. Not a math trick. This describes actual physical reality. You can't have space without time. You can't have time without space. They're aspects of the same thing. When you move through space, you also move through time. When time passes, you're moving through space-time. Even sitting still, every event in the universe happens at a specific location in space-time. Here's where it gets interesting. Space-time isn't rigid. It's flexible. It can bend, curve, warp. And what causes it to curve? Mass and energy. Every object with mass curves the space-time around it. The more massive the object, the more it curves space-time. Earth curves space-time around it. The sun curves it much more because it's way more massive. Even you curve space-time a tiny amount. Everything with mass warps the fabric of reality. Think of space-time like a stretched rubber sheet. Place a bowling ball on it. The ball creates a dip. The heavier the ball, the deeper the dip. Now roll a marble near the bowling ball. The marble doesn't travel in a straight line. It curves toward the bowling ball, following the slope of the depression. From the marble's perspective, it's just following the straightest path available. But because the sheet is curved, that path curves toward the bowling ball. That's gravity. Earth curves space-time. When you drop a ball, it's not being pulled by a force. It's following the straightest possible path through curved space-time. That path just happens to curve toward Earth's center. You're not being pulled down. You're following the geometry of curved space-time, the geodesic revelation. In flat space, the shortest distance between 2 points is a straight line. But in curved space, straight lines don't exist in the usual sense. Instead, there are geodesics, the paths representing the shortest distance between 2 points in curved space. Think about flights. The shortest route from New York to Tokyo doesn't look like a straight line on a flat map. It curves way up over Alaska. Looks weird on paper, but on a globe, it's the shortest route, a great circle route. In curved space-time, objects follow geodesics. A planet orbiting the sun isn't being pulled by a force. It's following a geodesic through the curved space-time created by the sun's mass. From the planet's perspective, it's moving in a straight line. But because space-time is curved, that straight line looks like an orbit to us. The planet is constantly falling toward the sun, but moving sideways fast enough that it keeps missing, a perpetual state of freefall. Picture yourself in an elevator. Someone cuts the cable. As the elevator falls, you'd float inside it. You wouldn't feel your weight. You'd be in freefall. Now imagine you're in deep space, far from any planet or star. You and the elevator are drifting. You'd also float inside because there's nothing to push against. These two situations, free fall in a gravitational field and floating in deep space with no gravity, are the same experience. You can't tell the difference from inside the elevator. Similarly, standing in an elevator on Earth, you feel the floor pushing up on your feet. That's weight. The floor resisting your tendency to follow a geodesic through curved space-time. In a rocket in deep space accelerating at 9.8 meters per square second, the same acceleration you experience from Earth's gravity, you'd feel the floor pushing up on your feet in exactly the same way. From inside the rocket, there's no experiment you could do to tell whether you're standing on Earth or accelerating in deep space. These two situations are equivalent, predictions that sound like science fiction. This leads to some absolutely insane predictions. Gravitational time dilation. Time passes at different rates depending on where you are in a gravitational field. The stronger the field, the slower time passes. Not a perception thing, not that time feels slower, time actually passes at different rates. If you had two synchronized atomic clocks and put one on the surface and one in orbit, when you brought them back together, they'd show different times. The one on the surface would show less time had passed. Sounds like science fiction, right? It's been measured many times. In 1971, scientists put atomic clocks on commercial airplanes and flew them around the world. When they landed, those clocks were ahead of identical clocks on the ground by exactly the amount Einstein predicted. The difference? Measured in nanoseconds, but real and measurable. GPS satellites have to account for this, or their position calculations would be off by kilometers within hours. The atomic clocks on GPS satellites run slightly faster than clocks on Earth's surface because they're higher up where space-time is less curved. Every time you use Google Maps, you're relying on Einstein being correct. Gravitational waves. Ripples in space-time. The 14th of September 2015, a date that changed astronomy forever. Both LIGO detectors, one in Louisiana, one in Washington State, picked up a signal. A gravitational wave had swept through Earth. According to Einstein's theory, accelerating masses produce ripples in space-time itself. These ripples travel outward at the speed of light, carrying energy away from their source. Imagine throwing a rock into a pond. Ripples spread across the water's surface. Gravitational waves are similar, except they're ripples in the fabric of space-time itself. As a gravitational wave passes through a region of space, it alternately stretches and squeezes that space in perpendicular directions. Einstein predicted gravitational waves in 1916, but thought they'd be far too weak to ever detect. He was almost right. The change LIGO detected was roughly 1/10th, zeroth the diameter of a proton, like measuring the distance to the nearest star to within the width of a human hair. The Mercury solution. Remember Mercury's orbit mystery from earlier? When Einstein completed general relativity in 1915, one of the first things he did was calculate Mercury's orbit. General relativity predicts that space-time curvature near the sun causes extra precession. When Einstein calculated the amount, he got exactly 43 arcseconds per century. The decades-old mystery was solved in an instant. Einstein later said, this was one of the happiest moments of his life. The cosmic web. General relativity doesn't just describe gravity. It describes the structure and evolution of the entire universe. In 1922, Alexander Friedman used Einstein's equations to show the universe must be either expanding or contracting. It can't be static. Einstein initially resisted this. He believed the universe was eternal and unchanging. Then, in 1929, Edwin Hubble observed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it's receding. The universe is expanding. Space itself is stretching, carrying galaxies apart. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward far enough, and everything was compressed into an incredibly hot, dense state. Dark matter and dark energy, the 95% we don't understand. When astronomers study galaxies, they measure how fast stars orbit the galactic center. Based on visible matter, stars on the outer edges should move much slower than they do. The only explanation? Additional mass we can't see providing extra gravitational pull. Dark matter. It doesn't emit light or any electromagnetic radiation. That's why it's dark. But it has mass, so it curves space-time and affects visible matter through gravity. Roughly 85% of the matter in the universe is dark matter. Only 15% is ordinary matter, the stuff that makes up stars, planets, and people. What is dark matter? We don't know. Leading theories suggest it's made of undiscovered subatomic particles that don't interact with light or normal matter except through gravity. Scientists are building detectors deep underground to try to catch dark matter particles colliding with normal atoms. So far, they haven't detected anything conclusive. The search continues. Dark energy is even more mysterious. In 1998, astronomers studying distant supernovas made a shocking discovery. The universe's expansion is accelerating, completely unexpected. Everyone assumed gravity would gradually slow the expansion over time, but acceleration suggested something was pushing the universe apart, counteracting gravity. This mysterious something is called dark energy. It appears to be a property of space itself. As the universe expands, creating more space, there's more dark energy. This drives faster expansion, which creates even more space and even more dark energy. A runaway process. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter is around 27%. Ordinary matter is about 5%. We live in a universe where 95% of it is stuff we don't understand. That should be humbling. The future of gravity. Where is gravitational physics headed? The Event Horizon Telescope continues observing black holes, looking for any deviations from predictions that might hint at new physics. Gravitational wave detectors are becoming more sensitive. LIGO is being upgraded. New detectors are being built in Japan and India. And LISA, the space-based detector, is planned for the 2030 seconds. LISA's sensitivity to low-frequency waves will reveal supermassive black hole mergers occurring when distant galaxies collide. Each detection adds another data point, confirming Einstein's equations work even in the most violent events the universe produces. There's also the quest for quantum gravity. Several experiments are being designed to probe the interface between quantum mechanics and gravity. These are incredibly challenging because quantum gravitational effects are expected to be significant only at the Planck scale, approximately 10⁻35 meters, 20 orders of magnitude smaller than a proton. We can't build particle accelerators that reach those energies, but there might be subtle effects we can measure indirectly. And here's the thing. Despite general relativity's success, we know it's incomplete. It's incompatible with quantum mechanics. We need a unified theory of quantum gravity. String theory and loop quantum gravity are leading candidates, but neither is confirmed. Until we have a complete quantum theory of gravity, there will be aspects of the universe we can't fully understand. The big picture. General relativity has fundamentally reshaped our understanding of the universe. It's not just a better version of Newton's theory. It's a completely different way of thinking about space, time, matter, and gravity. And it's been confirmed by every experiment and observation to date. One of the great intellectual achievements of humanity. One person, Albert Einstein, sitting and thinking, working out the implications of a few simple ideas, constructed a theory that describes the cosmos from the smallest scales we can probe to the largest structures we can observe. But the story doesn't end here. We know general relativity is incomplete. We're still searching for a deeper understanding that unifies it with quantum mechanics. We don't understand dark matter or dark energy, which make up 95% of the universe. We don't know whether the universe is finite or infinite, whether it will expand forever or eventually contract, whether there are other universes beyond our own. These are open questions. The universe still holds mysteries, and that's exciting. There's more to discover. Here's what you should remember. First, gravity isn't a force in the way you've been taught. It's the curvature of space-time. Objects follow geodesics through curved space-time. When you feel weight, you're feeling electromagnetic forces, preventing you from following your natural geodesic. Second, space and time are unified into space-time. And space-time is dynamic, curving in response to mass and energy. This beautiful interplay gives rise to all gravitational phenomena. Third, general relativity has been confirmed by countless experiments. From Mercury's precession to gravitational waves to black hole images, every test has supported Einstein's theory. Fourth, despite its success, general relativity is incomplete. We need a theory of quantum gravity to fully understand the universe at its most fundamental level. Fifth, these ideas have practical applications beyond GPS. Understanding gravity helps us understand everything from star formation to the large-scale structure of the cosmos. And finally, there's something profound about understanding that we live in a universe of curved space-time, not just an abstract mathematical concept, the fabric of reality. Every moment of your life, you're moving through space-time, following geodesics, experiencing time dilation relative to other observers, interacting with the curvature created by Earth and the Sun and the galaxy. You're part of a vast cosmic dance that's been going on for 13.8 billion years and will continue for trillions more. When you drop your phone and watch it fall, you're not seeing a force pulling it down. You're seeing it follow the natural geometry of space-time. When you look up at the moon, you're seeing an object in free fall, endlessly circling Earth, because that's the geodesic it follows through curved space-time. Right now, as you sit there, you're not being held down by gravity. The ground is accelerating upward into you. That's what weight is, the floor constantly pushing you up, preventing you from following your natural geodesic. In free fall, you're weightless, because you're finally free to move along that natural path. You've been in free fall your entire life. You just didn't know it, because the ground kept getting in the way. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We're tiny creatures on a small planet, yet we've figured out the fundamental laws governing cosmic scale phenomena. We've measured the curvature of space-time. We've detected ripples from black holes colliding a billion light years away. We've imaged the shadows of black holes at the centers of galaxies. And we're not done yet. The universe still holds mysteries. Dark matter, dark energy, quantum gravity, the ultimate fate of the cosmos. But we're figuring it out, step by step, discovery by discovery. And you're part of that journey.